Hello dear friends, welcome to my channels. Today's discussions is property of connectedness. So friends, let's start to discuss the property of connectedness. I hope I explain everything in my connectedness video. This is the abbreviation and very short note. So let's start to discuss connectedness. Let x comma tau be a topological space. Is said to be a connected if and only if there exists g comma h there exists g comma h belongs to, in here also belongs to tau such that g does not equals to phi, h does not equals to phi, g intersection of h equals to phi, and x equals to g union h. X is said to be connected if and only if it is not disconnected. Example, every indiscrete space is connected. Number 1, every discrete space is disconnected if the space contains more than one point. If x equals to a, b, c, d and tau equals to phi x comma a comma b, then the topological space x comma tau is connected. The empty set phi and the singleton sets x are assumed to be connected. The set R with usual topology is connected. If x is disconnected, then G union H is not unique representation of x. That is, there may be many representation of this type. If x comma tau is disconnected, then there exists a non-empty disjoint open set G belong comma H subset of x and G union x equals to G union H. G union intersection H equals to phi, then G equals to x minus H, G is closed, and if x comma tau is disconnected, then there exists non-empty disjoint closed, H is open. Similarly, G intersection H equals to phi, H equals to x minus G, H is closed. So, if x comma tau is disconnected, then there exists non-empty disjoint closed set G comma H subset of x such that x equals to G union H. A topological space is totally disconnected if given any pair of distinct points x, y belongs to x, then there exists a disconnection G union H of x with x belongs to G and y belongs to H by the property of Hausdorff space. Totally disconnected, that implies Hausdorff space. Disconnected space provided the space has more than one point. Disconnected space provided the space has more than one point. A one-point space is connected as well as totally disconnected. Let x comma tau be a topological space and a subset x, then the set A is called maximal connected subset of x if A is connected and A is not proper subset of any connected subset of x. Number 4, a subset B of a topological space x comma tau is called component of x if it is maximal connected subset of x. If every indiscrete space has only one component, namely the space itself, let x comma tau be a discrete space, let x belongs to capital X be arbitrary, then x is connected. Singleton set X is connected subset of X. Hence, by definition, singleton X is component of X. From the it follow that each point of a discrete space x comma tau is a component of X. Let x comma tau be a topological space and a subset of X. A is called arc-wise connected. A is called arc-wise connected if for any 2 points a comma b belongs to A, there is a path f such that I tends to X from A to B such that if I subset of A. Let x comma tau be a topological space and x subset of X be arbitrary, then X is locally connected if and only if every open NBD G of X and there exists connected open NBD X of X such that X belongs to H subset of G. That is to say, X is locally connected if and only if the collection of all connected open and neighborhood H of X such that X belongs to capital H subset G. That is to say, X is locally connected of open NBDs of X from a local base at X. The union of two disjoint open interval on the real line is a space which is locally connected but connected. The union of two disjoint open intervals on the real line is a space which is locally connected but not connected. Similarly, there are topological spaces which are connected but they are not locally connected. Does not imply connectedness. Locally connected does not imply there are topological space which are connected but they are not locally connected does not imply connectedness. Let x comma tau be a discrete topological space containing more than one point, then X is disconnected. For each X belongs to capital X and set X, singleton set X is open connected set containing X and thus X is locally connected but not connected. Let x comma tau be a topological space and let I be the set of all real numbers belonging to the closed 0, 1 with usual topology. Let a comma b belongs to X be arbitrary a continuous map f such that I tends to X with the properties f0 equals to A, f1 equals to B is called a path from the point A to the point B. In this case, A is called initial point and B is called the terminal and final point of the path. A map f such that X defined as fx equals to P and for all X belongs to I is called constant path at P. For f is constant map and hence f is always continuous. Important result. Two closed subsets of a topological space are separated if and only if they are disjoint. And two open subsets of a topological space are separated if they are disjoint. If and only if they are disjoint. Suppose A, so first is closed, two closed subset of topological space are separated if and only if they are disjoint, and two open subset of a topological are separated if and only if they are disjoint. Suppose A and B are separated subsets of topological space x comma tau. Suppose C and D are non-empty subsets of X. That is C subset of A and D subset of B, then C and D separated sets, and A topological space X is disconnected. That implies there exists a continuous map of X onto the discrete 2 points space 0, 1. A matrix space X is connected if and only if every continuous functions f from X to 2 point discrete matrix space is constant. Let X comma tau be a topological space, then X is disconnected if and only if there exists a non-empty proper subset of X which is both open and closed. A topological space X comma tau is a connected if and only if the only non-empty subsets which is both open and closed in X is X itself. A subspace of real line is connected if and only if it is an interval. A subset A of real line are containing at least 2 points is connected spaces. Number 8, the set R of real numbers with usual topology is connected space, and the set of real with usual topology is connected. Let X comma tau be a topological space and a subset of X is disconnected if and only if it is union of two separated sets. Let X comma tau be a topological space and A be a connected subsets of X such that A subset of B subset of A, then B is connected and A is connected. And 11. Let X comma tau be a topological space and A subset of X. If A is connected, then A closure. This is the A closure. A closure is connected and the closure of connected set is connected. So the closure of connected set is a connected. A continuous image of connected space is connected space. A continuous image of connected space is connected space. The range of a continuous real valued function defined on a connected space is an interval. Number 3, f such that X tends to R is a continuous map, then fx is an interval where X be a connected space. Let number 13, let A index of alpha and such that alpha belongs to del be a family of connected subsets of topological space X comma tau such that intersection of A alpha belongs to the del is connected set. Let A equals to AI be a connected subsets of space X such that no two numbers of A are separated, then B is union of AI is connected. Number 14, let A alpha be a family of connected subsets of topological space X comma tau such that one member of the system intersect every other member, then alpha belongs to del and A alpha is connected. The component of a totally disconnected set X are singleton sets in X. The components of a totally disconnected space are its points. Suppose X comma tau is a topological space and E subset of X if any 2 points of E are connected in some connected subset of E, then E is connected set. Solution. Suppose X comma tau is a topological space and E subset of X if any 2 points of E are contained in some connected subset of E, we claim E is connected set. Suppose not, then E is expressible as union of non-empty subsets G comma H subset of X that equals to G union H and G bar intersection H equals to phi, or G intersection H bar equals to phi, and G comma H does not equals to phi. There exists phi belongs to G, there exists P belongs to P, small p belongs to G, and small q belongs to H. That implies P comma Q belongs to E for G union H. That implies there exists subset of E such that F is connected, and P comma BQ belongs to F by initial assumption E equals to G union H, F subset of E. That implies F subset of E implies F subset of G union H. Now F subset of G union H, F is connected, G, H are separated sets. That implies F subset of G or F subset of H. That implies P, Q belongs to G, P, Q belongs to H. Also, P belongs to G, Q belongs to H. That implies G intersection H does not equals to phi. So contrary to the fact G intersection H equals to phi, contradiction. Hence our assumption E is disconnected is wrong. Hence our assumption E is disconnected is wrong, so that it is connected. So E is connected. Friends, in here we can say one note, important note, a topological space. This problem is this way: a topological space X is connected. X is a topological space X is connected. Topological space X is connected if and only if for every 2 points in X there is some connected subspace of X. There is some connected subspace of X which contains both 2 points. Prove that the union of two non-empty separated subsets of a topological space is disconnected, and prove that a set A is connected if and only if A is not union of two separated sets. Solution: let A and B be separated subsets of a topological space X, tau. To prove that A union B is disconnected, our assumption implies that A does not equals to phi, and B does not equals to phi. Number 1. Number 2, A bar intersection of B equals to phi, or A intersection B bar means B closure equals to phi. Number 3, A subset of B equals to phi, that implies A subset of B equals to phi. Write X minus A bar equals to G and X B bar equals to, therefore A bar and B bar are non-empty closed subsets of non-empty closed subsets of X, that implies G and H are non-empty open subsets. Non-empty open. This is the important non-empty open subsets of X. Then G union H equals to X minus A bar union X minus B bar equals to X bar minus A bar intersection of B bar. Now A intersection union of B intersection of G equals to A union B intersection of X bar minus A bar means A closure, and here it is just X, okay, not X bar, equals to A intersection X minus A closure union A intersection, not A intersection, B intersection X minus A bar equals to phi union B equals to B. A union B union H equals to A. Similarly, for union B equals to phi, that implies B subset of X minus A bar A closure, and for B intersection of X minus A closure equals to phi. Not phi, it is it is not phi, I can't say, it is B, because X minus B subset of X minus A bar, so it is B intersection of X minus A bar equals to phi. It is not equals to B, not phi, and A subset of A closure, obviously, that implies X minus A closure subset of X minus A, that implies A intersection of X minus A closure subset of phi, that implies A intersection X minus A closure equals to phi. Now A does not equals to phi, does not equals to B, that implies A union B A union B intersection of G does not equals to phi, and A union B intersection H does not equals to phi. According to this equation, I give some equation number A intersection B. This equation I will tell 1, equation number 1. This equation A union B, this equation and this equation and this equation. Which equation? This equation A union B intersection G equals to B. This equation and this equation equals to 1. According to equation, this equation I can say 2. According to equation 2, A union B and intersection G, A union B intersection G, intersection A union B H, A intersection B equals to phi. A union B intersection G union A union B intersection of H equals to A union B equals to phi. No, sorry, it is not phi, it is just A union B. It is does equals to not phi, A union B. This is. So after that, finally we have shown that there exists G, H belongs to tau such that A union B intersection G does not equals to phi, and A union B intersection H does not equals to phi. A union B intersection G and intersection A union B intersection H equals to phi, and A union B intersection G union A E union B intersection H equals to A union B. By definition, this proves that G union H is disconnection of A union B. By definition, G union H is a disconnected. G union H is disconnection of A union B, and hence A union B is disconnected. It is not union of two separated sets. Next example, let x comma tau be a topological space and A subset of X, G union H be disconnections of A, then show that A union G, A intersection G and A intersection H are separated sets. So start our solution. Let G union H be a disconnection of a subset A of a topological space x comma tau. To prove A intersection G and A intersection H are separated sets. For this, we must show that number 1, A intersection G and A intersection H does not equals to phi. Number 2, D A intersection section G intersection A intersection H equals to phi. Number 3, A intersection G intersection D A intersection H equals to phi. Our assumption implies that G comma H belongs to tau such that number 4, A intersection G does not equals to phi. A intersection H does not equals to phi. Number 5, A intersection G intersection A intersection H equals to phi. Number 6, A intersection G union A intersection H equals to A. 5 implies 1. To prove number 2, suppose not. This implies D A intersection G intersection A intersection H does not equals to phi. That implies there exists X belongs to D A intersection G and X belongs to A comma X belongs to H. That implies H is an open set containing H is open set containing X such that X is limit point of A intersection G, and that implies H contains points of A intersection G other than X. That implies A intersection G intersection H does not equals to phi. That implies A intersection A intersection G intersection H does not equals to phi. So that A intersection G intersection A intersection H does not equals to phi, which is contradiction of 5 or contradiction of contradiction of 5. We say this is phi, contradiction. So hence let x comma tau be a topological space and y subset of x. If y is connected, then so is y bar, means y closure is also connected. Alternative, the closure of connected set is connected. The closure of connected set is connected. This is the alternative proof. Particular case of the previous theorem, since y subset of y closure and subset of y closure, but due to importance we shall give an independent proof here. Let y be a connected subset of topological space. Let y be a subset, be a connected set, y be a connected set of a topological, y be a connected set of a topological space x comma tau. To prove y bar is connected, a comma b subset of x such that a bar intersection b equals to phi and b bar intersection a equals to phi. Let y bar is disconnected. B bar intersection a equals to phi and y bar equals to a union b, and a union b equals to y bar subset of y is connected, and this implies y subset of a or y subset of b, y subset of a, that implies y bar subset of a bar, that implies y bar subset of a bar, that implies y bar intersection b equals to phi, y bar subset of a bar intersection b equals to phi, that implies y bar means y closure of y bar intersection b subset of phi, that implies closure of y intersection of b equals to phi. A contradiction, we get contradictions, so hence proved, so that we can say closure of a set, closure of a connected set is a connected. Now we will discuss, show that a totally disconnected space is a T2 space. So T2 space means Hausdorff space. Let x comma tau be a totally disconnected set so that give a pair of distinct points x comma y belongs to capital X. There exists disjoint open set open set G comma H subset of X such that X equals to G union H, X belongs to G comma Y belongs to H. By definition, this proves that X is T2 space. Show that the total disconnection space is T1 space. Total. Proof since x comma t tau be a disconnected x comma tau is disconnected space and x comma y belongs to capital X, there exists disjoint open set G comma H subset of X and X equals to G intersection H, X belongs to G and Y belongs to H. By definition of T1 space, T1 space, okay, T2 space or T1 or T2 space, you can say T2 space. Now X belongs to G and G intersection H equals to phi. That implies X does not belongs to H, Y belongs to H. So G intersection H equals to phi. That implies Y does not equals to G. Thus we get X belongs to G, Y does not belongs to G, Y belongs to H, X does not belongs to H. It follows this that X is T1 space. Thanks for watching, friends. I hope I can make more video like this kind of topological video. I will create more topological